So, hi everyone. I hope you enjoyed coffee. um, is it working? All right. Maybe I could put this a bit higher. Best. Okay. Well, so in this presentation, I will summarize to you our paper entitled Characterizing Distributed Mobile Augmented Reality Applications at the Edge. This paper is a collaboration between TUM, University of Hulu, and NTNU. In this presentation, hello? Okay, maybe you can also close the door at some point. It's a bit noisy. All right. So in this presentation, we'll discover the challenges and opportunities of architecting and orchestrating augmented reality applications in edge environments. Let me start with a quick introduction of, first of all, why specifically augmented reality and why edge? As we also saw in the previous session, edge computing, one of the main advantages of edge computing is that by bringing computation closer to the user, we are able to reduce the latency. Augmented reality, as a matter of fact, is one of those use cases that requires very low latency. And in order to achieve high accuracy in our application, we need to deploy a big model that require a lot of computational resources. And in order to do that, edge computing seems like the natural way of proceeding. So we can deploy these applications at the edge, achieve low latency and high accuracy. The problem is, though, that in order to do so, we need a scalable design, applications that are flexible and that are portable. And here comes the distributed part of the issue. So at the edge, we have heterogeneous resources with different capabilities, different GPU. So the availability of the hardware is difficult to predict in general. And in order to deploy this sort of application, we need to consider the virtualization technologies that we are using in such a way that we can flexibly deploy this application, and also the way the application is actually designed, and in such a way that we can exploit the possibility of distributing specific pieces of functionalities across the available hardware. And on top of that, it's extremely difficult to measure the quality of service and quality of experience of the application, because when we deploy this in this kind of environments, we have only access to high-level metrics. So we don't really know how the application is really performing. In general, the approaches that we see out there in the literature are either monolithical approaches, where we see the functionalities of the augmented reality application bundled in a single container or a single virtual machine, or approaches that actually tackle the distributed aspect, but for custom deployments and don't take into account the possibility of the infrastructure provider being a different person than the actual application developer. So they lack consideration regarding the automated deployment, the distribution, so far, so forth. In our work, we try to go kind of in the middle, and we transition from this sort of approach to a fully distributed approach, where each service is packaged independently. And as you can see here, we use Scatter as an example application. We use a literature-driven approach to design this application. So starting from what's out there, we designed this as a fully offloaded augmented reality application, where a client sends the frames to the first service, which is primary. Primary service performs downscaling and grain scaling of the frame and sends the frames to the SIFT microservice that performs feature detection and extraction. Then the frame is sent to the encoding microservice that performs PCA and Fisher encoding. The encoded data are sent to the LSH service. We perform nearest neighboring on the encoded data. And then at the end, the data from SIFT and LSH are sent to matching. I would like to point out here that SIFT, first of all, is a stateful service because it keeps the feature extracted data internally, because this data are heavyweight and therefore difficult to carry around the network. And secondly, that as you can see here, we have non-linearity in the pipeline, meaning that matching at the end has to collect data from LSH and SIFT. And this nonlinear pattern is actually something that we find often in the literature. And therefore, we now want to analyze how this pattern is actually behaving in an edge infrastructure. So finally, when matching finally collects all this data, renders the frame, and sends to the client a frame that is augmented with the bounding boxes, detected objects, and the matching of the frames, so that the movement, the tracking of the frames of the object across the frames. Sorry about that. So in this case, we have fully offloaded approach. We have a pipeline where each component is independently deployed and replicable and nonlinear interaction. So the main question is, how is this performing? In order to do that, we create a setup where we have an edge cluster and a cloud cluster, and we orchestrate the components using orchestration system. In order to keep the presentation short, I won't be able to show you the results in the cloud, so we'll mostly focus on the results that we have at the edge, where there's different machines that have different architecture and different GPU. And in order to do so, we use Orchestra, which is a lightweight hierarchical orchestration system designed for edge. Main question would be, why did you use Orchestra and not Kubernetes or K3s? Main advantage of Orchestra here is that it's extremely lightweight, and with this very low footprint, enables application. So we release more of the resources to the application instead of to the orchestration system itself. We perform the deployment with different configurations. So we'll try first to deploy all the application on the first machine, then all the components on the second machine, and then we'll try to split the functionality of the application on two different machines. In particular, we deploy the Swift service first on the edge machine number 1 and then on the edge machine number 2, simply because they have different architecture and we would like to capture the impact of the different performance of the application in the actual end-to-end performance. We start with some baseline measurements, right? So this is the raw performance of the application when we don't scale any of the services and we just increase the number of clients without scaling the application. So this is the application as good as it gets. And we see a very, very bad, let's say, decrease in the general performance when we increase the number of clients. The decrease in performance is almost linear. So as an example, you can see that we have around 28, 29 frames per second with one client. With two clients, we drop at around 15. So this seems that the maximum throughput that we recorded was around 33 frames per second. And with only 85% performance, 85% success rate. Main question is, can an orchestrator capture the decrease in performance of this application just by looking at the high-level metrics? Because in this case, we are looking at a quality of service metrics, such as frame per second and end-to-end latency. We see that the end-to-end latency is actually 40 milliseconds, which is acceptable, but the general frame per second is decreasing a lot. Unfortunately, an orchestrator system by itself can only look at these high-level metrics, such as CPU consumption, GPU consumption, memory, maybe can know something about the network. And as you can see here, we notice a very counterintuitive pattern, actually. So when we increase the number of clients, so it means that the ingress frame per second goes from 30 frames per second to 120. The global CPU and GPU consumption is actually decreasing, except for one service, which is Swift microservice. So just from here, the orchestrator cannot really tell where the bottleneck is. After further analysis, in our paper, we discovered that the bottleneck is, as it was possible to anticipate, the Swift microservice. And the main reason for this is that the nonlinearity in the service dependencies causes Swift to be a bottleneck, because we receive double the amount of requests in this service because of the statefulness. And the next question is, okay, but if we scale the service, can we actually compensate for this performance degradation? Unfortunately, the answer is no. Because by itself, with this nonlinearity in the dependencies, when we scale up the services, we are amplifying the back pressure that we put on the pipeline. As a matter of fact, scaling up, we only achieve 10% improvement in performance in 2 to 3 client scenario, and the general performance actually decreases in all the other scenarios. So I would like to point out that even though we had an application and we split this application into multiple independently deployable microservices and independently scalable, the application is still behaving as a monolith. When we scale up the services, we are not really achieving the scalability that we were hoping to. And in order to have full scalability, we need full replication of the application. So with this in mind, what did we learn so far? First of all, as also pointed out from the keynote on Tuesday, hardware utilization alone doesn't tell us much about the application performance. We need something more powerful. We need some sort of awareness of the actual application quality of service and quality of experience metrics. And moreover, the congestion in the inbound service interface caused most likely by the non-linearity in the dependencies of the service can really affect the scalability and the performance of the application. With that in mind, how can we re-architect the application and how can we improve the general performance when developing this sort of applications? Let's see if I can go forward. Okay, I was able to. So starting from the design, the initial design we had, we can transition to a version of the application that is completely linearized. The drawback of this approach is that now we put more pressure in the network because we are transferring the shift state from shift to every following service in the pipeline. Therefore, we more than double the size of the packets that we are sending in the network. The pros of this approach is that now each service can be replicated and scaled independently. Moreover, we would like to exploit one of the main features of augmented reality applications. Augmented reality applications are extremely low latency, and this is true, but it's also true that they have an important property. When a frame is too old to be processed, it's not worth processing it any longer. So if at any point in any service we receive a frame that for whatever reason, network latency or latency in processing is old, we can discard it and save processing time for frames that are more relevant. For this reason, we introduce a sidecar component together with each application. So without even changing the application or model optimization, we simply introduce this sidecar that performs thresholding in the frames and queues the frames between each service. And when receiving a frame, it analyzes, is it worth computing? Is not worth computing? If the answer is no, then the frame is thrown away. So with these modifications, we replicate the experiments from before. So this were where the results were before. And we go from the previous result to this, meaning that simply by changing the way the application is composed and the way the application, the microservice interact with each other, we are able to achieve 2.5 higher frame rate and plus 17% of success rate. All of this comes with the cost of additional 10 milliseconds latency. This is mostly caused by the network pressure. So the fact that we are transferring bigger frames and the queuing operation at each stage of the pipeline. But now the main advantage is that we can scale the service independently. So what happens with the same hardware as before, so without extending or scaling the cluster, what happens if we scale the services? This picture is a bit complicated. The main takeaway is that we scaled the number of clients from 1 to 10 this time. And using the same hardware and the same model as before, we were able to transition from a max throughput of 30 frames per second to 120. And so this outlines that the application is now behaving completely different compared to before. And the maximum frame rate is now 2.8 times higher. So what did we learn so far? Right, the application awareness is key. And in particular, components such as the queue presented before can be used to interact with the orchestrator platform, sending metrics such as the real-time thresholding, so how many frames we are discarding, the end-to-end latency, and the real-time behavior of each one single microservice composing the application. Nonlinear dependencies should then be avoided. Most of the time it's worth actually linearizing in order to achieve more flexibility in the way we distribute the application. And the fact that in general, we can exploit properties of the application itself to improve the performance. In the case of AR, we can discard easily frames that are old enough in order to save computational capabilities. Things we did not consider in this work are optimization on the model itself. I know we can do batch processing to process higher amounts of frame for each batch. And these are all optimizations that are possible regardless of the way you architect the application. You can do also optimization from the network point of view. For instance, media protocol, you can have further smart way of doing compression. You can also use tensor mapping to optimize your cluster and to reduce the memory footprint on the GPU for all the microservices that we are deploying. So many things are still possible regardless the design aspect of the pipeline itself. With that, I conclude my presentation. So if you have any questions, I'm happy to answer.
Thank you. So any questions for Giovanni? Oh, so I'll start. Yes, maybe one over there.
Hello, thank you for the nice talk. So can you say regarding, like, for example, at page number 4 or page 16, so the microservice, it's a process inside the one host, or they're connected to within different hosts? If the yeah, so this each microservice, it's instantiated in a single host. If so, how hosts are connected? Is it with TCP/IP stack or InfiniBand, or can you say more about the setting?
Oh, about the setup for the experiment.
Yeah.
Okay, so I can probably refer to this picture then.
Oh, yeah.
Right. So we try to deploy these services in this different configuration, at least for the edge environment. So since each service is an independent container, and we deploy first all the containers on the first edge machine, then all the containers on the second edge machine. And then across the two machines, we deploy half of the pipeline on the first device and then half of the pipeline on the second device. And as you can also see, I'm not sure if I can point this out here, we reflect this nonlinearity of SIFT interacting with matching back and forth over here. So there is sort of the loop happening here for the microservice interaction. And so therefore, with this different setup, we highlight, first of all, how the services are, or the inference speed of the service across the different hardware, because those are different machines that will of course introduce different sort of processing latency, and also how this affects the network for the communication across the services.
Okay. So following up on this question, so you didn't take into account the network usage between the containers, because here they're on different edges, right?
Yeah.
The containers. So did you notice like a difference in performances between this setup and everything on E1 or E2?
Yes, there is. Actually, didn't have time to cover this in detail, but as you can see here, there are some differences in this case. We mostly analyze the end-to-end performance, okay. And in some cases, actually deploying everything on a single device can, since we are reducing then the network latency, performs quite good. But in general, when you distribute the services across different machines, then you are reducing the overall load on a single one. So there are some pros and cons from this perspective. In general, the latency is the lowest from when you deploy everything on edge machine 1, mostly because the inference speed there was quite fast compared to edge machine number 2. But the distributed setup, maybe I can point this. Okay. This was the setup with the lowest latency at all, which was around 40 milliseconds, where we have the inference distributed across edge machine number 2 and edge machine number 1. So in this case, we have a lower pressure for the inference, and also the networking didn't seem to have a large impact. So somehow the main recipe for this use case is that the faster you perform inference, the better the general end-to-end latency was. In an environment where you have different network conditions across the machine, then different consideration must be done, because in this case, the latency was fixed, was 1 millisecond, okay, machine to machine. If you have larger setup, then that must be taken into account.
Another question? No, okay, so let's thanks the speaker, and one last time, thank you.
Good morning, everybody. I present this work that is a joint collaboration with my advisor, Sergei Goninsky, and the help of Farzad and Christian from Klagenfurt University. Adaptive bitrate video streaming is a prominent application in internet in terms of traffic. And how does it work? We have a video that is stored inside a server, and this video is not stored as one file, but is partitioned in different chunks. And these chunks are encoded at different quality level. To higher quality is associated also a bigger dimension of the chunk. Then the client strives to download these chunks in order to show a video to the user. And the client, by a so-called adaptive bitrate algorithm, decide which quality of the next chunk he has to download. Unfortunately, this ABR algorithm can make mistakes. Indeed, I have represented here two possible mistakes that he can do. So, for example, he can underestimate the bandwidth, and so it will download a chunk at low quality while one of higher quality would have fitted better. Or what can happen is that it makes an overestimation of the bandwidth, so it will download a high quality chunk, but this chunk does not make in time to be downloaded. So what is the consequence of this is that the client will see his video freezing. Everybody of us actually have experience of this. And this freezing is called in our jargon stall. Why ABR does all of that? Because it wants to maximize the final satisfaction of the user from the video streaming session that is watching. And what I just said is the definition of quality of experience, which indeed is this metric that measures the satisfaction of the user. Now, as you may think, satisfaction is quite a subjective concept. So how can we measure it? Well, the most straightforward way is by using subjective assessment. So you show an experience, a video streaming experience to a user, which in return gives a feedback through a proper interface. In this case, I've represented a slider. And for the sake of clarity, I will define the experience in this paper and for this talk as a series of chunks characterized by some objective influence factor, which are variables, literally variables, that describe this experience by per se. These influence factor are a lot in literature, but for example, just to make you understand, one of them is the stall duration that I mentioned before, or for example, the image quality of each chunk. Now, as you know, in real video streaming setting doesn't work in this way, right? Because when you see a video, you are not requested to give back a feedback of how much you are satisfied. What actually happens in subjective assessment is that the experience is shown to a group of users that we will call raters. They score the experience, and this experience is that these scores are then averaged into a new metric called MOS, which, and I want to highlight this, represents an hypothetical average user. What we see here is just a piece of the total subjective assessment framework, where in input we have a big set of experiences, then a sampler, which is basically a researcher or the guy that set up the subjective assessment, select a subset of them, and they are iteratively shown to the raters. Then the MOSIS and the influence factor all together are used by a modeler to build a so-called QE model. The modeler is, for the majority of time, just a regression function, and the outcome of this subjective assessment is a QE model, which is the tool that is actually used for measure the satisfaction of the user. Instead of asking him to give me the feedback, no, they use the QE model directly. Indeed, this model is then embedded inside a ABR streaming system. Famous example of ABR streaming system that use QE model are MPC or Pensive, that also have been mentioned in the keynote talk. And then the video are crafted, generated based on this QE model, and they are watched by a lot of viewers. Now, what is important to notice here? Well, first of all, the viewer, the consumer, basically are, I don't know, million probably, but the model is constructed by just few people, few raters. Moreover, the QE model by per se is not representing not even the raters, because it's an average. So it represents an hypothetical average user. Next question is, can this model built in this way, this QE model, be accurate for all the viewers? So in this slide, we are representing the scores distribution of 32 users from Waterloo 4 dataset, represented as boxes, and we have highlighted in green the average rater. As we can see, the scores distribution of the viewer is quite distant, quite different from the one of the average rater. Moreover, in this paper, we defined as a typical viewer the 10% that are furthest from the median QE perception. 10% is not absolutely a hard threshold, but is just arbitrarily chosen by us. But it's in essence, these atypical viewers are the ones that are the most misrepresented by the average rater. So in conclusion, this QE model built in this way is inaccurate for a typical viewer. How can we cope with this problem? Well, one solution is to build personalized QE models. And actually, there are various options that we can follow for doing that. For example, we can use indirect feedback from the viewer, so we are inferring their QE by monitoring their behavior. Or we can use multiple reference group, where we associate a viewer with a smaller set of raters with similar taste. Or we can let the viewer to tune its own QE model. We considered all these possible options, but since they have been too complex or they do not lead enough accuracy, we have discarded them. So all in all, given this consideration, we came up with some requirements that we want from a solution. And so we want that the viewer that enjoyed the video session is also the one participating in its QE model building through a feedback. And we want this feedback to be explicit, expressible, and actionable. In one sentence, the viewer is the sole rater for the personalized model. So now this viewer actually is participating in a subjective assessment because he participates in the QE model build. So he gives score, gives feedback to experiences. And the question is, but is this feasible in a reasonable amount of time? I mean, how much effort are we asking from the viewer? This is what have driven our work. So we came up with our methodology called individualized QoE, which essentially is a new methodology for building personalized QE model requiring low effort from the viewer. How? By limiting the number of the subjective tests, the experiences to be scored by a small number, and how, even though giving a super high accuracy to the final model, and it achieves that by using an active learning framework, which adopt a new sampler and new design modeler. We call them random improved greedy sampling for the sampler and extended support vector regression for the modeler. Here, I'm depicting an overview of our solution, but in its essence, the sampler and the modeler iteratively interact with a viewer in the loop that gives the score to these experiences, and iteration by iteration, the modeler improves its performance. Now, I want to spend more time in explaining you how we design our sampler and our modeler. More specifically, I will guide you through the logical step that we follow for reaching our final design for the sampler. So, in this slide, we are depicting 315 experiences taken from Waterloo 4 dataset. These experiences are described by two influence factors, the total stall duration and the image quality, with values that are normalized between 0 and 1. And with symbols and colors, we are representing the score given by this user to these experiences. Green color represents higher scores and red color lower scores. Clearly, an experience with low stall and high image quality has more a score higher. What are we asking here is, how can we select 50 out of these 315 experiences in such a way that these 50 experiences represent at maximum the total number of experiences? Why we are doing that? Because this is a very important factor for giving a high accuracy to the final modeler. So One easy, on the left side, we have the same graph that you see before. Here is the case of the animation that is not working. One very easy possibility for selecting these 50 experiences is by taking them randomly. But unfortunately, as you can see, the experiences tend to be clustered along the axis, while in the middle, the space is quite empty. So random sampling is quick, but gives a very poor coverage of the influence factor space. How can we slightly improve this? We can use greedy sampling. In greedy sampling, distances into the influence factor space is taken into account. And so we can see that actually this is better in terms of coverage of the input space, but it has another problem. It is biased towards high scores because, as you can see, the green points are the majority. So in this case, we have a poor coverage of the output space, which is the score space. How can we improve this again? We can use improved greedy sampling, which consider distances into the influence factor space and also in the output space, the space of the scores. But we do not know in advance the scores that will be given by the user, right? So we need to infer them, and this is where the active learning part kicks in, because the modeler is used for inferring the output space in order to run the algorithm. Unfortunately, the modeler at the very beginning is not trained at all, so is not very good in suggesting to the sampler which experience to pick. And unfortunately, this algorithm is also quite complex, so we can say that it has an high complexity with initial small gain. So our final design for our sampler is a combination of random sampling for the first 10 experiences and improved greedy sampling for the remaining 40, for a total of 50 experiences. Now, those numbers came up after experiments that we ran in the paper. Moving to the modeler part, we call our modeler XSVR because it's a support vector regression that uses 10 different influence factors. And we proved in our paper through permutation feature importance technique that all of them are useful for the performance of the modeler. Going back and putting all together, we have the same, we have the design that I already showed you before, but in this case, you notice that the viewer and the rater is the same person, the red guy, and the modeler created is adopted by the ABR streaming system and is used for craft the video to the very same viewer that participates in its QE model construction. We envision our methodology to be used on a voluntary basis, so people that actually don't want to use IQE, they don't have to, because they can just use the general QE model that is already stored into the video streaming provider, and this is represented by the green guy. And moreover, we are expecting that the people that are the most incentivized to use our methodology are the atypical viewer, because they are the most misrepresented by the green model here. That's all for our design, and let's move to the evaluation part. So we develop IQE inside a server, and the viewers can interact with it by link, password, and username through which they can connect to our server. And to them are shown 120 video streaming experiences. Only 50 of them are used for training our IQE technique, while the remaining part are used for the evaluation. All the experiences are 8 seconds long because they are composed by 4 chunks of 2 seconds. And in total, we have gathered 120 real viewers leveraging MicroWorkers platform. The viewer interacts with our server through the interface that I'm depicting there. So basically, they move the slider and click a button. So what do we evaluate? Well, we compare the accuracy of IQE against traditional QE modeling More specifically, we compare IQE against 10 prominent QE models that span different possible designs. So we are going from exponential function to logarithmic to deep learning one. For example, B model, that the one that we call here B, is very popular in ABR video streaming settings because it's used by Pensive or MPC. And here we are depicting the distribution across all the 120 viewers of the mean average error, which measures the distance between the regression function and the ground truth data. We see clearly that the red line IQE outperformed the others. Quantifying this better performance, we can state that the average MAE decreases at least by 42% for all the viewers and by 85% for atypical viewers. And how much time is requested to them for reaching these results? Well, the total playback time of our 50 experiences is 7 minutes. Then there are some extra time, like for example, downloading the video per se by itself takes time. Thinking about the score takes time. Maybe the viewer wants to take a break in between, so it takes time. So in total, we have estimated that the time needed in median is around 22 minutes, which we think is a reasonably low effort. This is our most important conclusion, but we extend our evaluation section by doing simulation, specifically for evaluating the design choices, parameter sensitivity, and the overhead of IQE. And for doing this, we leveraged a new technique of synthetic profile, where we took 8 different trainable QE models and 32 sets of scores from real viewers. We trained the model with these scores of the viewer. In total, at the end, we had 256 synthetic raters, which are trained model. With them, we make them score a lot of experience quicker than real viewers. So in this slide is an example of sensitivity analysis that we conduct. So we fix the sampler and we change the modeler. So we are comparing SVR against random forest, extreme gradient boosting, and Gaussian process. And we see that across the number of experiences, the MAE of the IQE is constantly outperforming the others. We run similar sensitivity analysis also for other alternative design, and the conclusion is always the same, that IQE consistently outperform design alternative. Finally, in this slide, I'm showing you the per iteration time overhead of our solution, which in this case, this overhead is basically picking the experiences and training the model, removing all the time that the viewer wastes for think about the score and giving it. And what we want is that this time should be negligible, not perceived by the viewer itself. So even after 250 iterations, the total amount of time taken is around 0.15 seconds, which is negligible for the viewer. And we run a similar experiment also for the memory consumption, and we can conclude that the processing and memory overhead of IQE is negligible. In conclusion, IQE is a new methodology for building personalized QE model requiring low effort from the viewer. We evaluated it with 120 real viewers and extend the evaluation with simulation, and quantifying its improvement, it gives an increase of accuracy of 42% for all the viewers, 85% for atypical viewers, requiring just 22 minutes of their time. That's all. Thanks for the attention.
Thank you. Any questions? Yes.
Support. That was fun.
Thanks.
Pity about the lack of animation. I actually just got methodology question, which is, so the Likert scales, that's the really bad, medium, kind of moderate, good, oh, awesome, those sort of scales that surveys use. There's a lot of literature to suggest never leave a middle. I was wondering if you had a histogram of what the humans actually responded over that scale and how that compared with the robots, because I'm wondering if you've trained something that robots like and you just found the robots really like it. Do you have any insight to the original data? And also, have you considered making the cognitive load for the humans much lower by simply offering two choices, good, bad, no middle, good, bad, and then do the analysis on the basis of only two responses? Because humans quite like pressing a button that says good or bad and don't have to pick a cognitive load slider. Oh, that was kind of good, I didn't really like it, etc.
So if I have understood well, the first question is if the synthetic raters are similar to the real raters.
Yeah. And with the real raters, was it a distribution or was it a skew?
Okay, actually, we did this and we compare. I have a slide somewhere in the backup slides. I don't know if I can show you this one. Actually, here we are comparing the real raters against the synthetic raters in terms of correlations. And we see that actually they are quite similar, very much similar, if this is your question.
Well, actually, let me chime in. I think Andrew asked a lot of questions in one.
No, the second one.
So I think about the distribution of scores, for example. So we actually did the evaluation on the scale from 1 to 100. Well, partly when we started, we used Waterloo data set, which already uses this scale. Actually, we have a paper coming up in CoNEXT' next month. So actually, we show that actually, indeed, if you plot the histograms, you have a spikes of the scores. The scores divisible by 5. For example, 50 is most popular. So indeed, so I think actually one conclusion from this, not this paper, but kind of the subsequent paper, that you should use relatively small number of scores. Well, actually, the common recommendation is 5, right? If you look about MOS scale, it's 5. So I think that's kind of a wisdom we got from there.
Yeah,
and I think
just for saying,
yeah.
5 is not 2, as he was suggesting, right? Bad or good is maybe too simplistic. 100 is too much, probably. We have some insight on that.
And another thing you ask about, so again, most of the paper, most evaluation and the main results come from the studies with the real users. So the simulations in the second part is a kind of a supplement. And I think what you kind of anticipated is there as well. So if you look at the real scores, the error is much higher. So with the synthetic rate is lower, which is also kind of what you, I think, implied in your question. So if you, I know, create a synthetic user, then they become more predictable than the real users.
So thanks very much.
One
for the
last question,
presentation. I was wondering, did you consider audio quality as well? Because if you look now, so if you do streaming, audio comes in, let's say, 3 qualities, whereas if you stream, let's say, from YouTube, you have so many quality levels you can select from. True. And oftentimes you have stall, not because there is not enough video content, but you don't have enough audio content. Did you look at that?
No, we didn't consider the audio in this paper, just the video part.
Okay, thanks for the introduction. So yeah, I'm going to present the work I've done with 2 of my now former brilliant PhD students. They're still brilliant, but not PhD students anymore. Hao-Yu and Alec, and because of logistic reasons, they couldn't be here. So we basically took a reinforcement learning approach to kind of combat, circumvent network censorship, especially when the sensor becomes smarter and uses machine learning to do that. Hence the name. So the algorithm is kind of changing form to kind of bypass censorship. Okay, so I mean, censorship, it's of course, it's an ongoing arms race. So what happens typically, I mean, you're in a censored region like here. Yeah, so you're behind the firewall. You have traffic that is seen as benign, so the sensor will let it go onto the internet, and then you have tough traffic that you know is going to be perceived as sensitive because it has some political views, things to do with, I don't know, sexual orientation and so on. So the regime will say we'll block this. So what people do, they'll tunnel that traffic to some proxy nodes, which you can see here at the bottom, and then those proxy nodes will relay the traffic to the intended destination. So that's all good, but now we know that tunnel traffic has some distinct fingerprints, which are deterministic to do with packet size, protocol headers, packet size, handshaking information, and so on. And there's been a lot of work on this, actually. So there's colleagues Wu and others who looked at how the Great Firewall of China blocks encrypted traffic. Then there were other people actually working potentially for the Great Firewall of China, and under the sign of anonymity wrote a paper explaining how China detects and blocks shadow socks, which is another tunneling protocol using SOCKS 5. And then other people looked at how you use TLS. So basically you use HTTPS proxying, right? So you do TLS in TLS. Okay, so now it's fine. But when you move kind of, becoming more and more sophisticated, you as a sensor will say, well, what can I do? So you move from using pure deterministic fingerprints to using some statistical fingerprints. So you now start looking at the distribution of packet sizes, distributions of packet interarrival times, things to do with bursts, and so on. And of course, the research community kept at it, and there's been work on looking at how you can detect any sort of network protocol obfuscation when you can basically hide the protocol inside another protocol. There's people starting looking at how you can use machine learning, for instance, to detect whether you're tunneling traffic through a multimedia protocol. And then there's people who are looking at how you detect attempts by people to kind of avoid a website fingerprinting. Okay, so basically what's the whole system? How does it really work? Yeah, so you basically want to go online, you're behind the gateway, and then the sensor, what it will do, it will collect some traffic information, build some database with that. It will extract some features, things to do with, properties of packets in the uplink, downlink direction, and so on. What's their kind of standard size, max, minim, standard deviation, and so on. Burst size, interarrival times, protocols, and so on. And then it will use a classifier. And of course, now machine learning is kind of accessible. You can buy a GPU and train some very sophisticated stuff. And then you will use that classifier to kind of take a decision. Do I let this flow go or not? Okay. So now the question we tried to answer with this work was, well, how can we bypass that sort of censorship pipeline? So we took a little bit of inspiration from what people have done in the imaging community. So this is basically an example where basically you have a classifier that is kind of fairly confident that the first image is a panda. You add some noise to that image, and the result will be what you see on the right. So perceptually to a human, it's still a panda. Now the classifier is highly confident that this is now actually a gibbon. Yeah. So we thought, well, what if we do some perturbations to traffic so that the classifier believes that sensitive traffic is actually benign, which is exactly what we did. So your sensor basically controls all this part of the pipeline, yeah, which we discussed. Oh, okay, so some garbling as well, I guess. The slides were made on a Mac, but you've seen most. It's censorship, yeah, that's fine. But I mean, I kind of explained this stuff already. So the idea here is, okay, so if you're an adversary, you try to kind of circumvent the system. You either have a white box model, meaning that you have potentially some knowledge of how that classifier will work, which may or may not be true. So if you're an insider and you know what is being deployed, maybe you can share that information and so on. But most of the time, the attack model is a black box model. So basically, you don't know anything about the model architecture. You have no idea about what weights have been trained and so on. And you have no idea what features are being actually used to decide whether or not some flow is potentially seen as problematic. So even if you had a white box type of model, so what happens basically, packets kind of come on the wire, right? And this is, let's say, it's an example of sensitive traffic. So what you would say, well, actually, I can take that flow, project it into a feature space and add some noise. Remember that image? So I add some noise to this so that the new features now look as if this was kind of innocuous traffic. And then I will try to convert that back into packets. Well, there's a problem because this process is not guaranteed to be invertible. So actually, if you take meaningful traffic, transform that into features, perturb that features, and then you want to convert back into a real packets, those packets actually might lose their semantics. So if you just want to fool the classifier, fine. If you actually want to get some traffic through, well, it might not work. So we said, okay, well, we can do something about it. So typically, okay, I have a flow which is in the end a sequence of packets, as you see here, and that's sensitive. So the strategy we're taking is basically we try to learn the policy whereby we add padding to the packets, and actually we change a little bit the interval arrival time. And basically we do that as packets arrive. So we don't need to wait for part of the flows to kind of be captured or kind of be observed and so on, which is kind of natural, right? You don't really know how long a flow will be and so on. So you cannot collect all those statistics ahead of time. So keep doing that. And eventually with those manipulations, you want to kind of have at the end a stream that if it was kind of looked at collectively, the features would be basically looking as if that flow is not sensitive at all. So what do we require here in this process? So the first step is basically to do this obfuscation as you generate packets. So don't wait for the flow to terminate. And secondly, we want to make sure that by the time the actual flow actually terminates, it has been perceived as benign and it goes through. So that's where reinforcement learning comes in, because in the end, it's like similar to a gameplay. No, so if you're familiar with the game of Go, what do you do in Go? Well, you try to decide a sequence of actions that will eventually lead you to a winning position, just like, and that's going to give you back a reward. No, so you can kind of draw an analogy now. So you're thinking, okay, so I'm going to do a sequence of actions which are actually manipulations of packet sizes and packet timings at different steps, so that by the time the game finishes, in this case, by the time the flow finishes, the reward for me is that the flow has gone through that firewall. So how do we do that? So basically, yeah, this is kind of the whole sort of adversarial reinforcement learning principle. So you have an agent, which is basically taking your traffic, modifying it, and sending that to the sensor. And then you're observing the result of that. So that's basically what we call the environment. So I'll just take a little bit of time to kind of explain high level how this thing was basically the reasoning behind each of these components. And then if you're interested, you can read more details in the paper. So if you look at the environment, what do we really have here? So, I mean, I'm looking at some observations, which are the original packets, and I'm looking at the actions that I make as an agent, no? And I'm going to see what's the effect of those actions to this sort of censored environment. So I know this, I know the sensor will use some feature extraction. I have no idea what this look like, but there's a function. I know it will use a classifier, which basically will give me a probability score between 0 and 1, which is telling me whether the flow is benign or not. And then it will have a decision function, which is basically, it's like a decision boundary. Yeah. So depending on that probability score, it will say, okay, I'm going to admit this flow or not. So for me as an agent, what I can observe is only whether the flow, the last step. No. So eventually I'm going to transform that into a reward signal, which eventually is basically a function of all these things that I enumerated. So that will tell me whether I was successful, which is great. But the question is this fully practical? Maybe not. So what other things we looked at is, like, for instance, we looked at how application performance might be impacted. For instance, I don't want to delay packets forever because, for instance, if the traffic is kind of delayed sensitive, that's going to have some implications on that. So in the training process, we introduce a time overhead penalty and a data overhead penalty, meaning that I don't want to do too much padding because then again, I might have issues if I have a low bandwidth connection. And that's your final reward signal. So now that's how I look at the environment and now what the agent does. So basically, as I said, is you're trying to kind of decide these actions, like a sequence of modified packets. Yeah. So here we take a so-called actor critic approach. So the actor is basically trying to figure out what is the optimal strategy to generate those modified packets and timing between the packets. And then the critic is basically trying to evaluate the quality of these actions. It's as simple as that. I mean, each of them is a neural net and so on, but that's what effectively they do. So now, remember, I generate an action based on a state. So the question is, how do I generate that state? Because flows have variable lengths and so on. So the concept of state is becoming a little bit sort of fuzzy now, right? So what we did to kind of deal with that, we said, well, we're gonna take an encoder that will take flows of arbitrary length and map them to represent the abstract representation of fixed size, and then decode them later on. That's fine. But you only use the decoder part during the training, because eventually what happens in real, so once you train that end-to-end system, you only care about the decoder part, yeah? So you take the packets and then it's a sequence of them. You don't care how long it is, but then you map that to something which is of fixed length, and that gives you that uniformity to some extent. And the GRUs here are some gated recurring units, which are good because they exploit some temporal correlations which are inherent to the traffic that we're observing. So then we say, okay, this is nice. Now let's see if it actually works in practice. So how do we do that without actually having access to a sensor system? So what we did, we basically looked at two anti-censorship systems. We looked at Tor and we looked at V2Ray, which is basically TLS tunneling. And we crawled the top 25,000 Alexa websites with and without each of these tunneling solutions. And then we took that data offline. We used part of it to train a set of sensoring classifiers, and then part of it to train the actual agent. So mind you, here basically I don't know how the classifier was trained as an attacker, and the attacker doesn't know how I'm going to train my algorithm to circumvent censorship. And then we used part of that for validation and testing. So what did we choose for the classifiers? Obviously, I mean, there was feedback during the reviews like, oh, did you try this against the Great Firewall of China? And we thought like, well, no, because we can't reproduce. We have no idea what happens there, but there's some really solid literature we can actually build on. So there's been work on stacked denoising encoders that was presented at NDSS. There's the work on deep fingerprinting, which was a CCS paper. There's an LSTM that was used again for website fingerprinting. And then there was a paper at Using Security that looks at decision trees and random forests. And then there's another NDSS paper that basically uses, the solution is called Kumul, but eventually it's a support vector machine. So it's okay, let's basically try experimenting against each of them and see how well it works and how transferable the results are across different classifiers that we haven't seen before. And then, of course, you had to do some benchmarking, but importantly, just bear in mind, there is no existing work that actually does this sort of black box threat modeling using adversarial settings. Yeah, there has been work on white box modeling specifically for other domains. So there is this so-called Carlini-Wagner attack, which basically introduces perturbations. This needs GAN and then blind and adversarial perturbation. And I'm going to quickly show you some results with this as well and highlight why they're really not appropriate for this type of application. So let's look at what happens when you actually don't do anything. Yeah. So at the top you have Tor, at the bottom you have V2Ray, and then in the middle you see the performance of different classifiers, and you can see accuracy F1 score is really well. So those classifiers work remarkably well understanding tunnel traffic. So then, okay, you look at different approaches. So you can look at Carlini-Wagner, NIDS, BAP, and so on. They have a reasonably good success rate. However, they're really not kind of sort of stable. So there are some circumstances that if you take the stack onto an encoder, it works really poorly if it's stored traffic. Or if you take BAP, it works quite poorly when you have a deep fingerprinting approach. So you don't have that consistency. And then when you see not available, basically those attacks really kind of rely on gradient information, and those models are not differentiable. There's no gradient information that you can actually try to infer during the learning process. So actually you can't really craft a strategy. And that's where we come in, and things work pretty well. There are situations where I think some of the solutions were like marginally better overall. I think the performance we offer is on par with that of white box attacks, although we don't have any assumptions about how they work. And importantly, it also works with neural networks in which other classifiers are other attack strategies are really not suitable. Okay, so then just like before I finish up, just some other things. What you should have see here is also like some confidence bands, but then again, another glitch. So what we are looking here, the message is what happens if I don't get that reward signal, no? So I'm looking basically what is this attack success rate as a function of the reward masking rate. So if the reward masking rate is 0, it means I get back all the feedback. But maybe I get only 10% of the feedback, which is what you see at the right end of that x-axis. So here I'm showing 2 examples with random forest and cumul, which is the SVM. So obviously, if you don't get feedback, the training will be affected and some of that success rate will drop a little bit, but still it's kind of staying relatively good. I mean, it's around 80% or higher. So that's pretty good. The stuff in the brackets is, okay, how many queries you make, and that's again to do with computational complexity and so on. And I mentioned transferability. So I think this is a kind of a beautiful result. So basically what we did here, we said, okay, we trained the agent against one type of sensor. We didn't know anything about it. And then we took that agent and tested against a different classifier without knowing what it is. And this is like a perfect example when you can see actually some things actually work really well, but there are also limitations. So you can't really like go and expect that, you know, you'll have a solution that will be like a silver bullet, because that's not the case. But the takeaway message is here that if you have, basically, if you crafted adversarial samples against one certain type of classifiers, it's really likely that it will work against similar classifiers or classifiers that actually process similar types of input. And you see that for basically, that's the temperature detail is like the attack success rate, and you have Tor on the left-hand side and Vitoray on the right-hand side. And you see there are also some differences because the features within these 2 types of approaches are themselves different. So there's more results in the paper. We looked at what happens when you have different network environments. You have packet loss, which is not because the sensor wants to kind of mess around with you. We looked at how well that state encoder actually works, what features actually matter. And also we looked at which actions actually matter most depending on what type of classifier you're trying to attack, and many more. So just to summarize, a one-liner, in my humble opinion, this is the first black box attack targeting machine learning-based classifiers for network censorship. The code is online. We got almost all the badges, but the last one required quite a bit of work because now you have all the experiments. You have to train a lot of models, so it's kind of computationally expensive. There wasn't that much time. However, we have the pre-trained models on Git, so you can go and download and play with them. So with that, thank you for your time, and I'd be happy to take questions.
Thank you. Any questions? Yes. Oh, many.
Is it working? Okay. Thank you for the great talk. So I had a couple questions. So firstly, did you test it against, for example, the Great Firewall of China? Like, did you send actual traffic using this model? And the second question, that some of these protocols, for example, TLS, they're just censored based on some sort of a heuristic. For example, one of the recent papers that came out, it showed that it just converts all traffic to bits, and it literally just looks at the ratios of ones to zeros. And if it's more than 50%, if it's 50%, it just knows that it's randomized traffic, so it's probably TLS, so it just blocks it. So there, you might not need a lot of these machine learning models to kind of see if. So the Great Firewall doesn't really use a lot of these machine learning models in some protocols. So do you think your approach would work in that case as well?
Okay, so the first question was about whether we tested against the Great Firewall of China. And I think I alluded to that in the presentation. I mean, you can say the same did we try against the, the censorship system in Iran. So the problem with that is that we don't have control over what's happening in that box. So if you want to have reproducible results, it would be a little bit like, okay, I mean, you can set up a channel, a tunnel, and then try things out, and you'll get some results, but you will not be able to make any sort of meaningful conclusions because you don't have repeatability. You don't actually are able to run an experiment that's actually consistent. So no, I mean, it's just for that purpose alone, really. Whereas now with this, like, you can take the classifiers, deploy them, see how well it works, and if you want to circumvent the real system, you can go for it. The second question was about, I guess it's down to fingerprints, no? The fact that you might, yeah. So that's what I was trying to say in the opening. So even if you just like do plain tunneling, there are signatures. So for instance, if you take TLS tunneling, there is a at the beginning, you have a TLS handshake in a TLS handshake. That's a clear signature. So if you're able to play around with that, then it will just look as a single TLS handshake, which in the end, it's like you won't block it, right? Because for instance, 80% of web traffic now is HTTPS. So if you're a sensor and you don't have high confidence that this might be problematic and you try to block it, you might just basically harm user performance. And let's say you have an ISP behind that, they need to monetize, so it's problematic.
Another question, yeah, in the middle and one on top, and I think we'll take two more and that's it, yeah.
Thanks. Hi, Paul. Thanks for the presentation. This is Stefanos from Brave. My question is whether this technique would be applicable on lower level of the network stack. So if you don't talk about HTTP traffic and you go like lower level, like, different level of packages, would it still be applicable or not?
It could be. So one thing I didn't have time to show, and we looked at this in the paper. So what would happen if you want to run this in real time, let's say on a browser, no? So we gave some guidance in terms of how you basically embed that as a plugin into a browser. So for instance, sometimes, that the inference time, it's quite small, but let's say it's milliseconds or hundreds of milliseconds. But that, as small as it might be larger than the distance between two packets. And that's exactly what you want to avoid. So the proposal we had there was basically you can build some signatures at the beginning. So you can bootstrap the process early on. So you offset that latency and then you have a little bit of time to catch up with things. So by extension, I don't see why you couldn't go at a lower level and look at a bunch of other things. I think the principles still apply. It's just might be some specifics that will need to be kind of factored in, but should be. Okay, thank you.
Okay, we'll take last question and then.
Hello, so thank you for this interesting talk. So I had two small questions. One was that, do you think that still there could be some limits while working with real packets, because you cannot decrease their size, you cannot maybe change too much the inter-arrival time between packets and all. And a second was that you attack the classifier, but do you think classifiers can also attack your approach? Like if they see that how your approach works, then they can train another classifier which can.
Yes, so with the first one, so if you look at how tunneling works, actually, you have a client and you have a proxy. So the communication happens between these two endpoints. So it's kind of transparent to the end host. So as long as the two endpoints know exactly what's happening, there is no problem that, you pad packets or you add information that is redundant or you delay things, as long as you don't, let's say, break TCP state machines and delay things too much. So I think from a practical perspective, that's not a problem. I mean, I think this is kind of already deployed. For instance, if you just take vanilla Tor, I think packets are of fixed size right now, so they're being chopped. Yeah, so I think that's solved. Your second question was about the classifiers attacking you. Well, classifiers are typically passive, so they just basically decide on things. But what the sensor could do if they realize that somebody trying to avoid that, well, basically you can have, let's say, you can have a Swiss Army knife of classifiers and periodically switch between them. So part of the experiments we did with the transferability was exactly trying to see that. So, okay, if you train against one, how successful are you going to be against a set? I mean, in the end, there are some core structures to all of them. It's either, based on a random forest decision tree or is based on a temporal model. So they have commonalities. And we see that in those experiments that I showed. And back to my first point, it's an ongoing arms race. So eventually the sensor will try to, so the other experiment at the end where we're showing what happens when you have a mask reward, meaning that the sensor might think that somebody's trying to evade censorship and will just not send acknowledgements, for instance. And that might have an impact on your training process, but as I showed, it depends. It's not such a huge one.
Okay,
thank you.
let's thank the speaker one last time. Thank
Thanks
you
very much.
And
Hi to everyone. My name is Marco Rossanese. I am a research scientist in NEC, and this paper goes about reconfigurable intelligent surfaces in a production network. This paper was a collaboration with Telefónica in Masde in Spain. So for those of you who don't know what is an RIS or reconfigurable intelligent surface, this is a definition. They are man-made 2D nearly passive surfaces that can manipulate electromagnetic waves. They can be shaped in different waves, and you can interact with the waves in different ways. But in this case, I want to concentrate the attention only into one, and it's called passive beamforming, where you are able to collect the incoming waves, and then you're able to focus them and steer them where you want. So in this way, you are able to redirect your signals where they're most needed. Thanks to this device, we are able now to optimize the environment. Before, we used to tackle the environment as an enemy, and we want to adapt to it. But now the environment can play an active role, and we can optimize it as we would like. And somebody says that we are creating a smart environment. So we built from scratch our RIS prototype, and we simulated it, we tested it in a correct chamber, and we defined the radiation pattern of this device. So if you want to know more about all the process, I invite you to look at that paper that is referenced below the picture. So the goal of this paper is to analyze the benefits in terms of performance, and also assess the costs of RISs in real existing deployments in large-scale scenarios, for example, the City of London. However, there is a gap in the literature. There are only few papers that are dealing with this topic, and they are mainly theoretical and addressing indoor scenarios. Moreover, there are no radio planning tools that can integrate or embed this RIS object yet, and in a customized way. So we found this tool called Wireless Insight that is a ray tracer that is very handy and very flexible. And so we used that to analyze our case study. More about that later. So I want to start giving you some information about the cost model that we defined. This cost model is overly conservative because all the prices for RIS are based on our experience building these devices, and are based on retailing prices. So they are more expensive for what we expect in a mass scale production. Instead, for the base stations, we are comparing RIS to base station technologies. All the numbers are taken from the literature, and also were confirmed by our partner operator. So I'm about to compare two different RISs where we have 40 by 40 antenna elements, 80 by 80 antenna elements, two picocells where we shoot 20 dBm, a micro with EAB, so integrated access backhaul, where the micro is not connected via fiber optic to the backhaul, but via wireless. And finally, to a massive base station where we have 128 antennas. So from this table now, I want to highlight some of the most important values, in my opinion. And let's start with the base station and for the capex part. So the one-time cost that the operator has to sustain at the beginning. And the most expensive part is the connection to the backhaul, the fiber optics, followed by the tower. So the structure where you're gonna install your base station. Instead of the OPEX, so the cost that the operator has to sustain throughout the time to keep the system running, the most expensive entry is the consumption with 6.3K. These numbers are calculated with current price before the Corona crisis. So we expect this number to be even higher nowadays. Conversely, for the RISs, the most expensive thing is the equipment. So purchasing the RIS is the main factor here, and it's around 13K for the 80 by 80 and 3K for the 40 by 40. Instead, for the OPEX in the consumption, you can see that the costs are close to zero because RISs are meant to be passive and their power consumption is very limited. So if you now try to estimate the total cost of ownership, so the sum of OPEX and CAPEX over a time span of 5 years, we can visually see that a base station is more expensive than an RIS. More in particular, a 40 by 40 RIS can save you up to 80 by 88% compared to a micro, and a 8080 RIS can save you up to 78%. So it's clear that an RIS can make an operator save money, but how difficult it is to deploy them and how difficult it is to assess their impact on the existing networks. So we found in the City of London a great candidate because it is densely populated. The operator is investing a lot of money to guarantee good coverage to the users. And we are able to pinpoint some pain points on the map. So the operator has defined this threshold of RSRP. When you are below that threshold, the coverage is so poor that your connectivity is you cannot use them. You cannot use your mobile phone, for example. And this threshold is minus 100 dBm. And there are plenty of them on the city. But we found in this neighborhood called Hoxton, where there are several pain points. Although there are now 9 or 10 base stations split into 2 cell sites. So this is a good candidate to concentrate our efforts. So we imported this neighborhood from OpenStreetMap into Wireless Insight. We have a 3D representation. And then we deployed the base stations in the locations suggested by our partner. So we ran the simulation with Wireless Insight to understand how the RSRP is distributed on the map. And you can see that the best power is on the main road, that is cutting the map in half. And on the north part where we have a park, so it's an open space and the signal can propagate pretty easily. But on the left part, we have a residential area with a mixture of tall buildings, high buildings, and small houses. And there you can already see visually that the color is blue, violet, meaning that we have some problem there, some issues. So this is confirmed by the data sets of Telefonica. In these tiles of 100 by 100 meters, you can see areas where the median RSRP is below minus 100 dBm, and more or less they are located on the left side of the map. Therefore, at this point, we wanted to understand how reliable this ray tracer is. So we compare the median RSRP provided by Telefonica with results of Wireless Insight. And we saw that the RSRP error has a median error of 2 and 5 dB, but we define small enough to proceed with our case study. At this point, we defined 16 locations where we could operate by deploying an extra base station or an RIS. Deploying a base station is a known problem, so not big deal. But for a RIS, it's trickier because they are not supporting this kind of object yet, and they cannot import our knowledge of radiation pattern of our RIS. So we need to find a workaround for that. And basically, we are splitting the operation of RIS into two stages. The reception part, where we deploy the RIS with a size that we want, and then we analyze how much power this structure is receiving. And then we use that amount of power as input for the reflection part. In this slide, I want to give you some insights about the reception part. So we noted that as we are increasing the RIS size, more power we are receiving. And this is confirming the literature. This is not a big piece of news, but it's more interesting how the power is changing in relation of the distance from the source. For example, if we compare A and B, where A is at 150 meters away from the source and D is 600 meters and 650 meters away, the difference is around 10 dB. But if you compare A with C, where C it is at 250 meters away, then the difference is huge. And this is due to the fact that C is not very well located, doesn't have line of sight with the source. And therefore, there is nothing that we can do with that because it's getting secondary paths. So the takeaway message from this plot is that we can compensate distance with the dimension of RIS, but we cannot compensate improper location of the RIS in the system. So it's crucial to find a proper location for the RIS. Then for the reflection part, now I want to explain you the methodology. So first we take the region, the area where we want to intervene without any extra base station or RIS, and we use it as our baseline or reference. And then we deploy a 40 by 40 RIS and an 80 by 80 RIS, and in the same location, a pico, a micro, and a massive. All of them have the same orientation, so they have the same direction, they're pointing to the same point. And this is for the first scenario. In the same location, we steer the angle of RIS and the base station to another direction, and in the same way for the third scenario. So we are evaluating for the same location 3 different orientations. Then to evaluate the performance of an introduction of an RIS or a base station, we could see at the color of the spots. So you could already see from the plots that where we have a micro or an 80 by 80 RIS, we are doing better than the baseline. But to be more precise, we need to make another kind of evaluation. So what we did was to analyze spot by spot the baseline with another technology. And in particular, we were looking at how much gain in terms of RSRP we were getting and how many spots were recovered from below the threshold to above the threshold. So I want to start the analysis of the results with RSRP gain. I want to show you only 2 examples because to show all of them is not possible for the sake of time. So if you want to know more, I need to refer to the paper. And in this box plot, you can see the lower quartile, the upper quartile in the box, and the median in the center of the box. And the whiskers are representing the extension of the data. So in these 2 sides, P and H, the RIS is very well illuminated. So there is a good line of sight with the source. And I want you to concentrate between the comparison of the 80 by 80 RIS and the picocell, the orange plot and the azure aquamarine box. So in these 2 scenarios, in these 2 sites, The 80 by 80 RIS is dominating over the picocell, because even if the RIS is reflecting less power than 20 dB, especially in the P side, since the RIS is very directive, it can operate exactly where we want to intervene, while the picocell is more spread and is also sending a signal where maybe it's not necessary. So the RIS is more efficient compared to a pico. Then for the case H, where the 80 by 80 RIS is receiving around 20 dBm, then the RIS can compete with a micro and a massive base station. Of course, a micro and a massive are always an upper bound, so you cannot do better than that, but you can approach their performance. Then I want to show you this matrix called cost gain efficiency, that is variation of the SRP, the median SRP gain over the total cost of ownership. So basically in these plots, the operator can tell if what benefits are they getting considering the investment they have to sustain. And the VRIS is winning this metric, especially the 40 by 40, surprisingly, would be the best deal for the operator, because the impact is significant, but the amount of money you have to invest is pretty low. Then for the other results analysis for the coverage gain, so here we analyze how many spots were below the threshold at the beginning, in the baseline, and how many spots were recovered after applying an RIS or a base station. And it's possible to see that in the same size as before, that the 80 by 80 RIS is doing better than a picocell, especially in E, where the situation was dramatic at the beginning. And applying a base station or an RIS is very beneficial to that area. While for H, you can see that the bars are smaller because the situation was really good at the beginning. So putting an extra base station or RIS is not making that improvement, but the RIS can compete also here with a base station. Similarly, as before, in the cost coverage efficiency, I analyzed the ratio between the recovered spots over the TCO. And also here, the RIS is winning on most of the sites, except with C, where the situation of where the placement of RIS was bad from the beginning. And 40 by 40 RIS seems to be the best candidate also here. So to conclude this session, so our research provided the first estimation of RIS benefits in a large-scale radio environment, and for sure it's going to be a promising technology for the new generation of mobile systems. And to recap a bit the numbers that I just showed you, if we compare an RIS 40 by 40 or 80 by 80 with a micro base station, we can see that a 40 by 40 can reach the 23% of the performance of a micro base station in terms of RSP gain, and an 80 by 80 up to 65% compared to a micro. While for the mean area coverage gain that we can get, with a 40 by 40, we can reach up to 40% of a micro, and an 80 by 80 can reach up to 72%. And all of this can be done with the 12% of 5 years TCO cost of a base station, and for a 40 by 40, and 22% for an 80 by 80. And this is my last slide. So thanks for your attention. If you have any questions, I'm here to answer you.
Thank you, Marco. One question up front. Yeah.
Can you hear me?
listen to
Okay,
you.
okay, now, okay, fine, thanks. Thanks for the talk. I just wanted to understand, I mean, if I understood correctly, maybe you were working at 2.1 gigahertz, yeah? That's what you, and these are the size of the RIS in terms of elements, no? 80 by 80. So what about the physical dimension? I mean, how big they are?
So the 80 by 80, if I remember correctly, it's got a size of 6 meters.
6 meters.
Yeah. And the 40 by 40 is half of the size.
So the next question, is the mobile operator not complaining about that size? I mean, you have to mount that on the buildings, basically.
Yeah, I mean, this is not ready as a technology, so the operators are still understanding if it's worth or not to proceed with this technology. But the idea will be to, for example, apply them on billboards or on the facades of a building, so where you have space, and then you can cover them with, I don't know, canvas or other things to cover them.
Okay, but if they don't complain, it's good. I mean, okay, thanks.
And if you have multiple carriers, multiple operators, can they share the RAS?
So in our case, they're PETS antennas, so the bandwidth is pretty limited. So you are operating at the exact frequency that you want, and the rest you can ignore that because the impact of antenna is negligible. You could think about making an RAS for multiple operators, but it's trickier.
Because there's no control on the signals. I mean,
yeah, since they're passive, you can do whatever you want.
Okay.